Okay, so let us begin. So let me continue from where we stopped at the tutorial, in fact, yesterday. So you have by now, and you will today further calculate the mods for the Brilliant quiz data. And we saw that this is the drawing I had yesterday already to illustrate how to find a mods in a given initial data set. And we ended up with this equation for the mods. So let me call it h of theta like in the tutorial. So we had r to be h of theta, and this was some function of theta, right, which you calculated. Okay. And then the question is, what do we do with this mods now? So we have now identified, I've now explained to you what a mods is, and I've explained to you how to locate it in the initial data set, and you've worked it out and you will do so further today. So there's a few things of interest here, okay? So let me just explain that starting off with the easiest cases. So we have this initial data set. The topology was the following. So I had two wormholes here. Right? So this is for black hole number 1, and this is black hole number 2. And you also calculated, in fact, that the data is asymptotically flat at the two punctures and also, of course, at large distances. Okay? So the equivalent way of looking at this is that is the puncture sort of picture, Euclidean space. I have two punctures and I have the asymptotic region. But in fact, you realize from this that, in fact, each of the punctures is its own asymptotic flat end. Okay? So now the first concept I want you to understand here is the notion of an ADM mass. So that is so ADM stands for Arnovit, Dazer, and Misna. So what this is, it is trying to, so this is a definition of a mass and momentum, but we will not talk about momentum in this case, we just talk about mass. So this is the mass of the entire space-time, if you wish. Okay? So given, so in this situation, far away from these punctures, the data is asymptotically flat, so far away the metric becomes close enough to a flat space plus small corrections. And in that case, you can calculate, as I will show how, the total mass of this space-time. Okay? How does it come about? Well, so the metric, so Hij, so Ij are no spatial indices, I can AB, whatever, doesn't matter, will be the flat metric plus some order 1 upon r corrections. Okay? And we see already in the in our particular case, and you can also see that from the Schwarzschild metric itself, that this delta ij we saw in the isotropic coordinates was 1 plus m upon 2r to the power 4 times delta ij, right? So for large r, this is an approximately equal, so r is very large, so this quantity is very small, so therefore this becomes approximately 1 plus 2m upon r times delta ij. Okay, do you see that? Now, whenever the metric is, so this is a 1 upon r correction to the flat metric, so it's exactly of this form. And when you can write the metric in this form, then the number that appears here is called the ADM mass. Okay? There's a different expression for this, which is often used, which it's tied to any coordinate system, not just a spherical system like this, which is that the ADM mass says that you take a sphere of radius r and look at the limit of large radius, and the ADM mass is given by 1 upon 16 pi times the limit of the radius of the sphere going to infinity, and then you calculate this integral over the sphere, which is, so these are partial derivatives, so let me just, maybe it's, for people further back you can see this better. So del j of g ij minus partial I of g j j and then integrate that over dSi. And the sum over j, is repeat indices are summed over. So this is the same as that. This is just in a more sort of general sense. And is one of the main results in relativity that, in fact, the ADM mass defined in this way is always positive. Okay. So this was shown first by Schoen and Yao. And later by Witten using a different method that the ADM, this is the positive mass theorem, so which says the ADM mass is bigger than or equal to 0. And if it is 0, then the space must be Minkowski's flat space. Okay? So it's one of the main results of classical GR. And this applies here, so which means that this quantity m that appears, it has to be positive. So this tells you that the alphas appearing in the Brill-Lindquist have to be all positive. Okay? So then you see from the expression for the conformal factor, in fact, so in the case of the two black holes, right? So in that case, we have the H. Sorry, this should be Hij, not delta Ij, of course. So Hij for that case was 1 plus alpha 1 upon R1 plus alpha 2 upon R2 to the power 4 times delta. This was for the two black hole case, right? So then for the two black hole case, I can go far away here, calculate the ADM mass, and that would be essentially the sum of the two guys, right? So this would be alpha 1 upon 2. Yes. Well, so it would be M1 plus M2, where alpha 1 is M1 by 2, so M1 is twice of alpha. Okay, so this is just M1 plus M2. Now the interesting thing here is that, so this is the mass of the whole space-time. Okay? You can ask the question, what should the masses of the individual black holes be? After all, as you calculated, the black holes affect each other, right? The black hole one has a different, the geometry near it is affected by the other black hole. So A, should the mass of each of these black holes change depending on the influence of the other? And if so, how do we calculate it? Right? So as you realize here that these are asymptotically flat ends. So this is asymptotically flat, and so is that. So in fact, we can apply the ADM mass definition also at these asymptotically flat ends. So then you can define the mass of each of these black holes as the ADM mass measured at these asymptotic ends. And these do not have to be the same as M1 and M2. And these are not the same as M1 and M2. Okay, because as you see, there is an effect of the other black hole as well. And this you can calculate, right? Let's call them ADM masses of 1 to be M1, which does not have to be equal to little m1. Okay? And we can call the ADM mass at the other puncture to be, let's call it just M2 here. So this M1 and M2, big M1 and big M2, will depend on little m1, on little m2, and also the distance to the other black hole. And this you can calculate. It's not that difficult. So I'll leave it to you as an exercise to calculate then the ADM masses here using simply this definition here. You have to go to make the right coordinate changes like we did for the isotropic coordinates for Schwarzschild, and then you will then identify what the ADM mass is at these ends here. Okay? And then this was in fact the goal of the Brill-Lindquist original paper this was back in the 60s or 70s, I believe. So what they said was, well, the total ADM mass is in fact different from the sum of these ADM masses. This is what Brill and Lindquist found, which is that the ADM, the total ADM mass, is not the same as M1 plus M2. What should the difference be? Yeah, it's interaction energy. So in fact, the original Brillinkvist paper was titled Interaction Energy in Geometrostatics or something of the sort. Okay? So the difference of these contains the binding energy between the two black holes. And if you do that, you can show that this binding energy, which is M ADM minus M1 minus M2, is, again, it's a power series in 1 upon D. So this is G M1 M2 upon D. Okay, approximately, it's a minus sign there. Okay, so this was sort of the goal of the work, in fact, to determine what the binding energy should be. And using this definition, they obtained this, this quantity here. And this is not a difficult calculation. I would encourage you strongly to find the ADM masses of this at these two punctures, and maybe that should be one of the tutorial problems, if you wish. But it's not difficult, okay? So you can easily do it following just this definition here. Okay? Now, this raises further questions, right? So first of all, this is nice. It's a nice, one of the sort of important calculations of GR, and this is an important result also in GR. The question then becomes, how do we sort of generalize? This is a very special case. So we have applied this to this, conformally flat, time-symmetric data, and it may not always be that these ends are asymptotically flat. Because imagine that you set up initial data in this way, and then you let the data evolve and you solve it numerically. Then it's no longer guaranteed. First of all, it is not true that at later times the data is time-symmetric. It will not be time-symmetric. And secondly, the slice can behave in a strange way, so the asymptotic flatness of the slice is not easy to identify. It may not even be asymptotically flat. Okay? So therefore, this strategy of sort of going to these asymptotic ends and calculating this ADM mass will not always work. Okay? So instead, you can try a different approach, and this will sort of lead us now to this notion of isolated horizons and dynamical horizons and so on. What you can do is use this mods that you found. And to sort of motivate that, let's go back to the Schwarzschild case. So you know that for Schwarzschild, the mass is the radius divided by 2, right? And the radius is simply area divided by 4 pi, and the square root, and then 1/2 of that. So this is area divided by 16 pi. So this is known as an irreducible mass. For any black hole, given the area, calculating area by 16 pi, that is called the irreducible mass of the black hole. And then what you will show in the tutorial today is that in fact, for the mods that you found, you can calculate the area. It's somewhat complicated, but it's not in principle difficult. It can be done, and you will do it. Then you can define instead the masses of the two black holes using this irreducible mass of the mods. And you will find, in fact, if you now use for M1 and M2 the irreducible masses coming from the area, then you will find the same result. Okay? So this is to motivate you that there is something physical about this mods itself. So it is telling you what the mass of this black hole is without having to do the ADM mass calculation at these punctures. It is different at higher orders, yes. It will be different at higher orders, yes. And you're welcome to try and calculate it. It is not as different as you might imagine. So the difference only appears not even in you're doing up to 1 upon d square, but even 1 upon d cube is the same, and d to the 4th will start to be different. Maybe even higher. So I'm not actually sure at which order it starts to diverge, but they're quite similar to each other, in fact. Okay, good. Well, what I meant was that it won't be asymptotic flat at the ends. This will be asymptotically flat, the common thing. So that part is always there. What is not sort of guarantee in a numerical evolution is the nature of these punctures. What is happening to the space-time near those punctures? Okay, good. Yes? Which relation? Yeah, this is, you will show that in fact. So you can calculate the irreducible masses and you can then calculate this difference and you can see that it is in fact that. Yes. So now let me sort of proceed and present you some numerical results. So you've calculated with, I'm sure you've appreciated how complicated this calculation can be. And you can imagine going to the next orders and so on. You can continue as far as you want. And it'll get more and more complicated, right? So as the black holes come closer to each other, then the question is what becomes of these monsters, right? So let me now give you, present some numerical results on that, because as you can imagine, you cannot do this analytically beyond a certain point. It has to be numerically. But we're solving the same equation, but it becomes a complicated numerical problem to solve it, and I'll present you some results from that. Okay? Let me first sketch what happens, just by myself, so that you understand the results I'm going to show. So you have calculated so far the individual mods around the two black holes. I mean, you did it for one black hole, but the same applies for the other one as well, right? So you find them two separate mods. And there is this Euclidean distance d between them. Now there's two things you can study here. First is an artificial thing, which is that I just continue with the same initial data. I just make d artificially small, right? I can just calculate the mods. In this Brilliant quiz data, I can take the d to be anything alike. I just make the d smaller with the idea that, well, in a real black hole collision, the d will become smaller and the black holes will come closer to each other. So as a first step, we can simply try to calculate what the mods are as I change this d parameter in the Brilliant quiz data, right? And what happens is the following. So when d is large, I have two separate mods. And as they come closer, and as you calculate it, they start to sort of become distorted. So they get this theta corrections for the shape of the mods and so on. Okay? But when this d reaches a critical value, then what happens is that a common mods appears around them. Okay? And then, as you make then d even smaller, something very strange happens. This common mods, or the common apparent horizon that is often referred to, splits into two parts. One part continues to go inside. Let me use a different color for that. So one part continues to go inside, and the other part sort of expands outwards and becomes more and more spherical. Okay. So now as you imagine, as d, in the limit that d would be 0, there is just one black hole, there are not two black holes anymore, right? So in that limit, I must just have this outer one, which should be sort of the common horizon for both M1 and M2 together, right? And something interesting should happen, how this inner mods will sort of merge with these two guys, right? So let me show you some numerical results for that first. And the second thing that we will do, I'll show you the result of that as well, which is you can evolve this actually in time using numerical relativity simulations. So then these simple calculations are no longer true because at later times, the data is not time symmetric. So the extrinsic curvature is not 0 at later times. Okay? Then the question is what becomes of these mods under time evolution? Right? So let me first show the results for this, just changing this d parameter and see what happens to this, to these two mods. Right, so I've taken now a particular case in which I have the parameters M1 is 0.2, M2 is 0.8. So it's one particular case. It doesn't really matter what these are in effect, but the results are going to be similar for all of them. And at this particular distance, it turns out that you do have a common horizon. This is the smaller black hole, the larger black hole, and you can see that this common horizon is starting to split into these two pieces. They're very close to each other, but it's starting to now separate from each other. You can go further. And you see that now this blue one, the common, the outer, I'll call it the outer horizon. So that sort of becomes more symmetric. And the inner one is sort of moving inwards, and it is becoming more distorted. So it sort of has this weird shape. You can go further. And the outer one becomes really very symmetric at this point. And in fact, it essentially tells you the mass, the total mass of those two black holes at this stage. But the inner one is interesting here, right? It's become even more distorted as you go on. Now, there's one interesting fact of the Brilliant Quiz data, which is not true for non-time symmetric case, which is that we saw that these are minimal surfaces. And minimal surface cannot touch. So something very, very strange has to happen, not all of these. They're actually distinct. They're not touching it, even though it might seem like they're touching here, they're not. In sort of the actual time evolution, then they're no longer minimal surfaces because their extrinsic curvature is not zero, then they can actually intersect each other. But in this initial data, they cannot touch. So then this does all it can, right? Look what happens here. So these two remain as distinct black holes, the smaller one and the bigger one, and the green one sort of, wraps around them in this strange way. You can go even further. And this, at some point, this is sort of the neck between those two, right? So this is now, the green one is extremely distorted, right? Try calculating this analytically if you can. And this next shows the close-up of what is happening at the neck of this thing. So this is a close-up of this region here. Right, so this MOTS is sort of almost undisturbed, the blue one. The red one is distorted, but the green one, look at that. And these are the irreducible masses of all of these. We'll discuss this in more detail later. So I want to just show this numerical results here first. Now let us see what happens on the time evolution. This is just the initial data. Just change this d parameter, and this is what we find. So now let us look at what happens in the time evolution. Okay, wait, I'll play this numerous times just so that you can appreciate the, so let me first make it a yes. And let me go back to the beginning, okay? Okay, so here you see now what you're gonna see. Let me first explain what you will see, okay? So this one is a visualization in terms of just a slice through your space-time, okay? So this is the XZ plane. So the black holes are along the z-axis, so they will come closer to each other along the z-axis, and this is showing you the result along this slice of the MOTS. Okay. This one is the same thing, but just stacked up in time. Okay? Because each of these MOTS evolves in time, so over time it traces out a surface which is three-dimensional, and a sort of a lower dimensional visualization of that is here. And the actual MOTS is obtained is just rotate this around the other axis, then you get the full MOTS, if you wish. Okay? So this one shows sort of the time evolution, stacking up all of them and getting you the full three-dimensional surface, and this one is a slice of that, it shows you in 2 dimensions. Okay? So let us go through this slowly. So the black holes at this stage are far enough apart that I have 2 separate MOTSes here, or 2 separate apparent horizons. So they continue to evolve. And at this stage, again, just like when we change the d parameter, a common horizon forms. It splits into 2 pieces. One is the blue one that moves outwards, and the green one that moves inwards. Okay? And the blue one is always S outer, the green is S inner, and S1, S2 refer to the individual horizons. So now you see, as in the initial data case, the whole thing is as you might expect. So the green one becomes more and more distorted, and the inner ones, S1, S2, still remain spherical up at this point. And here you see sort of the interesting part here, which is this bifurcation. You know, when this common horizon splits into two pieces, so the geometry here is how that happens. So it is not like it's a discontinuous thing. It is like the whole surface is parabolic. So it's a smooth surface. Even here, the whole surface is completely smooth. It is like having a function which, so if I imagine a function like this, if I slice that here, I will find just one intersection. And if I slice it here, I'll find two intersections. Okay? So this is simply a higher dimensional version of the same thing. Okay? So all of these surfaces here, so this outer green one and this one and the individual ones, they're all completely smooth surfaces. So let's continue. So now you'll see a close-up of what is happening. So here now it's getting extremely distorted, this green one. And this shows a close-up of sort of this interesting region here. So you see then what happens is that the two individual horizons, the S1, S2, they penetrate each other, they go through each other. So the green, so the red and the magenta one, they are sort of intersecting each other. So then what happens to the green one at this stage? Well, it continues to exist, it doesn't just disappear, and it develops these kinks, these knots. And it is still a mod, it is still the same equation that you were solving. And it is still spherical topology. But it just has this self-intersection built into it. And you can continue further, and at some point we lose track of these horizons, but this tells you the basic sort of picture of these mods, how they behave under a merger. Okay, so let me play this one more time, the whole thing without interruptions. Now, what is not shown here is that, in fact, there's a whole zoo of these apparent horizons or these mods that are not shown here. And that would take us too far. That would be too complicated for our purposes here. So just, think of this as a basic first order picture, but there's further complications to this as well. Okay. So now you can ask the question, well, we have all of these things, and what do we do with it now, right? So the first thing is that, as we will now discuss in the rest of the course, so today and in the next 2 days, in fact, there is a lot of physical information hidden in how these surfaces evolve and how they grow. Yes? It's not, unfortunately. You can try. It's not. Unfortunately, it's not. You can try. I won't stop you from trying. So let me tell you, maybe it's possible. So try it. Okay, so let's. So could we move the screen back up so I can use the blackboard again from now? Okay, good. So now, based on these numerical results, I mean, the way I'm presenting this is completely not historical, right? So all of these things came much later, and things I'm going to present came earlier. So, but this is the logical order, I think, which makes the most sense. Okay. So you see now that we have found, you've calculated then these marginal trap surfaces, and you've seen a result of how they evolve in time. Okay. Then you can ask the question, well, is it even true that these mods should evolve always smoothly in time? So could it be that these are behaving very strangely, very wildly, and they can appear and disappear whenever they want? Yeah, if we can, yes, sure. Why, what is wrong? What would be unusual with M1 and M2 being the same? So nothing, I mean, in terms of the whole, nothing goes wrong in principles. You can do M1 and equal to M2 if you wish, yes. There are some things which are, in that limiting case, some strange things happen in the case of the equal, in this D parameter, but again, it's not physically important. There's no difference qualitatively with M1 being equal to M2. Okay, good. So as I was saying, so we saw that these surfaces evolve smoothly in time, but the question still remains, is it a mathematical fact that these should evolve in time, or under what conditions would this evolve smoothly in time? Okay. So let me for this present you a mathematical theorem. I had a notebook here, right? Where did I put it? There. Okay, so this is a result due to Anderson, Mars, and Simon. And this is, I think, from 2008, but I might be wrong about that. Something around that time. Okay, but this is an extremely important result mathematically, and it's a mathematical proof of the existence of these smooth evolutions of these things, okay? Or it tells you under what conditions that these will evolve smoothly. So the basic concept is the notion of the stability of these monsters. Okay? So the picture you should have in mind is the following. I have, let's say, a particular MOTS. Now imagine deforming this a little bit. So imagine that let me use a different color. Okay, let's use green. Okay. And this deformation I can parameterize as sort of moving along the normal direction, right? So it moves here normally and it moves here outwards. So then I can say that the deformation, for the deformation, I can say the deformation happens along the radial direction in the spatial direction. You can also think of deformations not on the slice, but in other time-like directions as well. That's also fine. That's also completely. But for the moment, let us just think of the deformation along this spatial slice, and I move at each point. I move it somewhere, some distance along the radial direction. Okay? So therefore, I can think of each of the deformations as some function times this radial vector. And the radial vector is the normal vector here, okay? So this is r hat, so at each point on the surface, I have this unit normal spatial radial vector. So I can say that I have f times r, that is the deformation of the surface. Okay? Then, for the deformed surface, I can calculate the expansion once again. Right? Now the condition is that for the original surface, the surface here shown in white, the expansion should be 0. Right? Then the question becomes, what is the expansion of the deformed surface? So I write that quantity as theta of f times r is the expansion of the same null normal, except now for the deformed surface, and that is now parameterized by f times r. Now the basic idea is the following. It is that if I deform it entirely outwards, so the function f is only positive, then the surface should become untrapped. If I deform it inwards, it should become trapped. And this is exactly what, in the simple Schwarzschild case, this is exactly what happens, right? If you go back to the Schwarzschild case and take any slice in the Kruskal diagram, so let me just draw that here perhaps. So take any slice like this. So look at now this intersection. So this will be some spherical surface. Imagine deforming it a bit outwards, so I move a little bit here. Then it should become untrapped because it goes into the exterior region. I can deform it inwards, then it should become completely trapped. Okay. And the basic idea of this result is that, well, as long as this property holds, then the surface will evolve smoothly in time. And a very nice way to phrase it is the following, which might seem a little bit counterintuitive, but let me just walk you through it. So this thing, the expansion of this deformed surface characterized by the function f, is in fact an operator acting on this function. So L is the operator and f is that same function that appears here. So think of this quantity as in fact an operation on this class of functions here. And then these people showed that in fact this operator has the following form. So L acting on, let's call the function to be psi, and the sort of, psi being like a wave function, so that will become obvious why I use this notation. So this is given by the following expression. The first term is a Laplacian. So this is not a Laplacian on this original sphere, right? This is the actual Laplacian with the actual induced metric on this. So it's not some background, it's just the actual, elliptic operator on this two-sphere. Plus there is a term here, I'll explain what this operator is. This omega is some vector defined on this sphere, and this is connected to the angular momentum of this horizon. And this d tilde is the derivative operator, the connection on this two-sphere. Okay. Then I have the other terms. Sorry, d of psi. Then I have the terms linear in psi, and that is 1/2 of the scalar curvature on this sphere, plus so let me explain what these terms are. So this is the scalar curvature, intrinsic scalar curvature on the sphere. So if it's a round sphere, then that's a constant. So this is the divergence of the same vector that appears here. And that vector happens to be the following. This will play an important role now in the rest of the lecture. And in their notation, this vector is defined to be this is like the cross sort of extrinsic curvature between n and L, okay, the two null normals. And this is a derivative sort of on the two sphere. So this is, I call it a d here, or d tilde here, if you wish. And finally, this sigma is the shear of the null normal L. Okay? So as we discussed last time, the sigma is the symmetric trace-free part of the extrinsic curvature along the L direction. Okay? And I told you that, well, this is a bit like gravitational radiation, the nature of the shear on a symmetric trace-free tensor on a two-dimensional space. So this, in effect, is sort of the radiation falling into the black hole, or the energy contained in that. Okay? Now, one thing is, when you study quantum mechanics, then you will come across Hamiltonians of various kinds, and these are all self-adjoint operators in that case. Here, this term prevents this from being self-adjoint. If you remember your momentum operator, right? It's I times d by dx, right? This I makes it self-adjoint. Without the I, it's not. And there is no I in this case here. Okay? So the whole operator is not a self-adjoint operator, which means it does not necessarily have real eigenvalues. And the question here is, well, given this operator, and look at its eigenfunctions, and with complex eigenvalues, are these eigenfunctions positive or not always? Or if they are positive, what does it imply for the time evolution of the whole thing? So the main result of what they showed is that, first of all, it turns out, in fact, even though this does not have real eigenvalues, its lowest eigenvalue is always real. I'm not proving that for you, but this is simply a fact in this case. And what they showed was that if this lowest eigenvalue is positive, it's not zero, then in fact, it is stable. In other words, if I deform it outwards, the expansion is always becomes untrapped in that case, and then the evolution can proceed smoothly. Okay? And in fact, it's in fact, they don't state it in that original paper in this way, but in fact, the actual result can be strengthened a bit. And the statement is that if this operator is invertible, in other words, if at any time none of its eigenvalues are zero, then the evolution can proceed smoothly. Okay? So roughly speaking, L invertible, which for the lowest eigenvalue corresponds to the stability of this, in this sense, that it means that a mod evolves smoothly. So this is the mathematical result. In fact, as I will show in the next lecture, most likely, that you can actually calculate the spectrum of this operator, the numerical simulation that we are doing. And you can look at its eigenvalues and see when it crosses zero, any of these crosses zero, and you can sort of understand the properties of this behavior even in that situation. So this is sort of the mathematical result, but the actual, in reality, it's even stronger. The mods even exist even when the eigenvalue becomes zero. Okay? But this at least tells you, what do you expect that? So this is sort of the mathematical basis for the whole thing. So any questions about that? Do you understand the basic concept of this result? Yeah, okay, good. So that would take me into sort of the actual details of this calculation that they did and the theorem they proved. So you have to accept that what they did, the way they proved the theorem was that they expressed the mods as a graph in a suitable high-dimensional space. And then the thing being invertible is like the function being sort of, a y is a function of x, and x is a function of y, inverse function theorem. And that can only be done if this derivative of the function is not, it's not vertical. So this is the condition here. So in fact, this invertibility is exactly that condition. And it turns out that when this is invertible, then you have a smooth surface in time. So it is using what you might have learned in analysis as the inverse function theorem, and so this is an application of that in a high-dimensional space in functional analysis, but it is the same concept here as well. Okay, good. So with this, at least then you can be satisfied that it is mathematically sensible to talk about this, this world tube of the modsas as they evolve in time. Okay? And this will now lead us to the notion of these different local horizons, so dynamical horizons or isolated horizons. So this is the reason why, in fact, you expect these to exist mathematically. Okay? So now with that in mind, let us now focus on sort of this evolution that we saw and this world tube of horizons that we saw, right? So in this diagram now, time goes vertically upwards. And each of the cross sections is a MOTS. You imagine there is some spatial time slice here, which evolves in time, and each time, each cross section of this would be a MOTS. And for these MOTSes, the expansion of the outgoing null normal has to be 0, and the ingoing one may or may not be negative. Generally, it is negative, but may not be always. Now, what happens is that if you go back to the Schwarzschild picture, so you have the same situation here. So you have, again, this, you can think of this as the time evolution of the MOTS, right? So this whole surface here. I can take different time slices, and if I evolve them in time, I will get this surface here. And Thomas talked about killing horizons, right? So he, in that approach, they try to sort of make the definition local. It doesn't require global properties, but these are still two strong conditions. So as today what we'll discuss is we'll try to weaken this condition to the minimal that is required and still proving interesting results from them. Okay? So this example is to say that when the black hole is static, it is not evolving in time, then the horizon is null. By horizon now, I mean this world tube of these MOTSes. But in the example that we saw, it is not always null. In fact, when the black holes are growing, then there is always some radiation falling into the black holes, into the horizons. In that case, the horizon is not null. It can be space-like or it can be time-like, it can be very complicated behavior, and that we will discuss possibly in the last lecture. So today we will discuss the case when the horizon is null. So this is the case when the black hole is close enough to being isolated, so there's no infalling radiation at the horizon. And that is what is referred to as an isolated horizon. Okay? So the general topic then for the rest of the lecture is isolated horizons. And the situation when the black holes are actually growing in time, so it's not time independent, so that is referred to as a dynamical horizon. And that we will discuss, I hope, starting in the next lecture. Okay. So today, let me now discuss the case when I have a three-manifold of this kind, which is null and which is foliated by marginally trapped surfaces, and understand the geometry of that. Okay. So any questions before we start this? Any questions up to this point? Yeah. So, sorry, could you say it? Well, this is not an initial value question here. This is the question of the evolution. Okay, it is connected to initial value problem. It is connected to that, but this is an operator on the sphere, on a compact space. Right? So this operator acts on functions living on the MOTS. So it's an elliptic operator because of this. This is the Laplacian. And so that's all it is, right? So I mean, you shouldn't sort of make it, generalize it beyond that. It is simply an operator acting on the sphere. Does that answer your question, or was that not what you had in mind? No, this is not an evolution operator, no. This is, as I said, this is, the operator is this, right? There is no time derivative here in principle. Okay, good. Any other questions?
We define apparent horizon as the outermost marginally outer tapped surface.
Right.
So in case of stationary black holes like Schwarzschild, there are no tapped surface, right? Means there the apparent horizon is the same as event horizon.
Yes, but
So
there are...
what is the definition of apparent horizon in that case?
Right, good question. So there, what happens is the following. So think of us, again, let's go back to this Kruskal diagram here. So think of a slice perhaps like this. So on this slice, this would be the outermost trap surface, right? So then this would be the apparent horizon on this slice. But if I were to choose this to be the outward direction, then this would be the apparent horizon. Okay? And if you go inwards, there will be fully trapped surfaces here. But you should be careful because even in Schwarzschild, you can think of very strange slicings of Schwarzschild, which would be, think of slices which at some angular points are in this region and at some angular points are in this region. Okay? On such a slice, there would not be any marginally trapped surface, but there would still be the intersection. So think of, it's hard to sort of visualize that here. So at some angular location, the surface is like this. At some, it would be like this, let's say. Okay? Then this is the intersection with the event horizon, except that it goes into the white hole region. But still, there is the null normal is L here, so you would still find a MOTS, except that the ingoing expansion, the theta n, which would then be here, in this portion, the theta n would not be negative. Okay, so in Schwarzschild, it's a simple except when you think of these weird cases. And yeah, so this is the situation with Schwarzschild. Okay. Any other questions? Yes, so as I said, so the extrinsic curvature will be non-zero at later times. So the data is not time symmetric at later times. It's only at initial data that the extrinsic curvature vanishes. At later times, it will be non-zero. The evolution happens in the submanifold. Then how does it affect No. The evolution happens in the full space-time. Again, this is maybe an important question. So what we are doing is we are evolving the whole space-time, right? So we have a slice here. We have the data on this slice, metric extrinsic curvature, evolve that in time. So the evolution happens in a full three-dimensional or 3 + 1 dimensional case. And from that, we can calculate where the mod should be located at each time. It's not like the evolution happens just on the mod. The whole space-time is evolving. Okay? Any other questions? Well, the definition requires that they be null. So you can ask whether they exist in actual case or not, and they do, in fact. But I'll give the definition in a minute, so you'll learn all about that in just a few minutes. But yes, it should be null. Any other questions? Yes. Yes, will be the same formula applies to also collapse situations. And the Vadya is one simple example of that. But you can make it much more complicated, right? In a collapse of a star, you will again find a formation of a MOTS. And it will evolve in time. And at some point, it will reach equilibrium. That's when isolated horizons apply. And before that, you will have dynamical horizons in the MOTS. But it all applies completely also for the collapse situations, yes. No, let me repeat one more time for the 1000th time now. Only in the initial data is the extrinsic curvature 0. Once it evolves in time, you don't control that. It is non-zero at later times. It is taken into account. So again, the extrinsic curvature is 0 only at the initial data, at t equal to 0. At any other time later on simulation, it is not 0. But you can still find the MOTS. I mean, the MOTS equation is still, it's completely valid, right? It's not that, I mean, you have the extrinsic curvature term, then that is taken into account, of course. Okay, so this seems to be a new recurring question. So again, the extrinsic curvature is 0 only in the initial data, and that is just for simplicity purposes here. Otherwise, you cannot do any of the calculation you did by hand. Okay, it's simply not possible. At least not possible by me. Maybe some of you can. And the reason I started with Brilliant was that you can actually do these things, in a relatively easy way by hand. And you don't need these numerical simulations for that case. Okay? Beyond that, there is no restriction on any of this for zero extrinsic curvature. It can be anything it likes. Okay, is that clear? Okay, so now I will describe the various definitions involving our-state horizons. And the reason that I do it like this is to sort of make the conditions more and more stronger, start with the weakest condition and make it stronger and stronger till the time that, and tell you for each case what results can be proven with that, okay? So this, if you like, what I'm going to talk about now is to extract from the notion of a killing horizon the weakest conditions required that still enable you to prove suitable, interesting physical results. Okay? So the first definition is what is called a non-expanding horizon. So we'll call that always NEH. So this is a three surface. Let's call the surface delta. So delta has to have topology of sphere cross, let's say, some interval of the real line. And it has to be null. Okay. The second condition is that the expansion of the null normal, which I call L, has to vanish. And the third condition is that the energy conditions hold and the field equations hold at the horizon. So this is more technical, and this we will use maybe not in too much detail in this lecture, but it is still in the definition, okay? And among the energy conditions, the weakest one we require is the weakest condition we need is that the Ricci scalar of the whole space-time contracted with the null normal L. So this has to be future directed and has to be causal. Okay? This is implied by the strong energy condition and null energy conditions as well. Okay? So this is what is called a non-expanding horizon. So this is the minimal structure you need to talk about the sort of this three surface formed by a MOTS in the case when there is no infalling radiation. Okay, so the simplest example is Schwarzschild, but you can have many, and Kerr is also in this category, and you can have more complicated examples as well. Okay? So if we were to imagine the Schwarzschild spacetime with not infalling radiation, but radiation sort of transverse, this would still hold. So this would still be null, and you would still have radiation sort of going in this way, but not falling into the black hole. Okay? And there do exist solutions of that kind as well. In an actual numerical simulation, it's a good approximation usually. So it's in fact a very good approximation. If you're even a bit far away from the merger part of that whole thing, for the rest of it, it is in fact very close to being isolated, a non-expanding horizon. Okay? So it might seem like a simple definition, but in fact it is very, very useful in almost all parts of the black hole merger, except in the very, very close to the merger. Okay? So again, the simplest condition, as we said, we want it to be a three-dimensional surface with cross sections which are spheres. So that is topology S2 cross some real interval of the real line. It has to be null. So that is this condition, there's no infalling radiation. Then the expansion has to be zero. That is sort of foundational, right? We require that each cross section is a MOTS. That is the theta L condition. So there is no condition on theta n here, as you might have noticed. Okay. So the cross sections are Motz's. They don't have to be marginally trapped surfaces. Okay. So any questions about this definition? It's a simple definition, but it's very important and it's has many consequences which we'll not discuss. But any questions about it? So this is a restriction. You could change the S2 to be a torus. You can take different topology if you wish. This is the simplest one of most practical use in all physical cases of interest, in fact. Yeah, it's evolving. So this is the time direction if you wish. So at each time, so it's good. So I could say S2 cross R, but that's an infinite line, right? So it's a finite portion of that. So the last condition is that the energy conditions are required to hold at the horizon, and we require that the Einstein equations hold also at the horizon. And that Einstein equation might seem like an obvious thing, but it is sort of useful when you look at a phase space calculation where you go sort of off shell, you go away from the solutions to the Einstein field equations, you still require that at the horizon, the field equations hold. So that's more a technical thing, so don't focus on that too much. But the energy condition, in this case, phrased in terms of the curvature, so that is still required. Sorry, say it again? Null energy condition needs to. Yeah, just a null energy condition, yes. Yes. We will discuss that in a minute. So in fact, that's an important question. And what you can do as a little exercise, if you wish, go to the Schwarzschild case, look at the horizon. So you might imagine the first question that you might have is, well, let's say this is the Schwarzschild horizon, okay? Normally we have a time coordinate, the V coordinate perhaps, right? Then you get some spheres like this. Now you could imagine that I take a different slice in time. So I can take, in fact, a very, very strange slice like this. So you can change your V coordinate to depend upon theta and phi. You may define a new V coordinate which depends on theta and phi, and that defines a slice of the horizon. And it is not obvious, but in fact, if you calculate the expansion of this, it is still 0. And even more, it has the same area. So area is completely unchanged. This may not be obvious, right? Because this surface looks very large in this direction. But what's happening is that, well, in this direction, the metric is actually degenerate. It's null. So by moving it here, you don't get any change in the area at all. This we will prove in general, but if you don't believe that proof, you can just go to Schwarzschild, just calculate it if you wish. It will be hard for complicated functions of theta and phi that you choose, but it is true. Any other questions? Because you need to understand these different conditions well enough, okay? So, because now we'll use them quite extensively in the rest of the lecture. Okay, good. So let's proceed. So the first thing of interest perhaps is the null normal L. So first of all, L has to be null, right? And that's by definition. So this L is along the null direction of the horizon. It's a null generator of the horizon. So it is null, and of course it is orthogonal to a surface, right? So it is surface forming. In this case, you can show, in fact, that L has to be geodesic. Not finely parameterized, perhaps, but it has to be geodesic. So that means that we must have So I'm not proving this for you, but it is in fact not that difficult. For any null vector field, in fact, which is, well, it's null, and it is surface orthogonal, or twist free if you wish, then it has to be geodesic. Okay? And this kappa is the surface gravity of the black hole. And at the moment, I still haven't showed you that it is, in fact, doesn't have to be constant, right? So I can choose any parameterization I like. And in general, this kappa doesn't have to be constant on the horizon. I could even make it a finely parameterized, in which case the kappa would be 0. So we can have, I mean, at the moment, the definition allows for all of these cases, but soon we will restrict ourselves further. Okay. Now the second thing, it is to apply the Ray-Chaudhuri equation for L. Okay. So this is essentially a component of the Einstein field equations, or in fact, just geometry at this, the way I'll write it. It is the following. So the Lie derivative of the expansion is kappa L, theta L, minus 1/2 theta L square, minus the square of the shear, minus LALB, plus the twist of L. So this is the Ray-Chaudhuri equation. And if you've never seen this, it's not hard to derive. Okay, it takes a little bit of work to derive it, but it is just follows from the definition of the various curvature tensors and so on. Okay, so this is the then in this equation, along the horizon, of course, theta is always 0. So this term is 0, this is 0, and this is 0. The horizon is, the L forms a horizon, so the twist is also 0. So you just have then these two terms have to be 0. And they both appear with the same sign, and that is important here. So it means that I have two positive things that are 0. This is positive from the energy conditions. So therefore, they must both be 0, right? So in fact, the shear has to be automatically 0. Okay? So automatically, just from this definition, it follows that the shear of L has to vanish. And this, in fact, is the condition that there is no infalling radiation across the black hole. Is that clear? So I used again the Ray-Chaudhuri equation. I set the theta to 0. I used the energy condition to say this is positive. And then that follows then that the sum of this and this has to be 0. So each of them is positive. This is manifestly positive here. Therefore, they must both be 0. Okay? Any questions about that? Yes, so this is the Lie derivative of this expansion along the L vector. So it's a time derivative. It's a derivative along the parameter of a fine parameter of L, and that has to be 0. Because it is 0 everywhere, right? So the derivative also is 0. Okay. Now the next thing. So given that L is expansion-free, shear-free, and twist-free, you can in fact show that so I will now make a little notation here. I will use this notation of an arrow on this to indicate that this index is pulled back to this null surface. Okay? Now here comes this point where you are to be careful about vectors up and the covariant contravariant vectors, or vectors in one forms, and which of them can be projected onto the horizon and not. Okay? So any index which is down, so and for any one form index, so that index I can always pull it back to the horizon. And that simply means that once I pull back, this can only be contracted with vectors tangent to the horizon. Okay, so that's all that means. And the reason this appears here is that, well, the expansion, the shear, and the twist apply to always the pullback of the extrinsic curvature of L, right? So that's why this index is always pulled back. So this would normally have the expansion, the shear, the twist, everything, right? In the present case, all of them vanish. So the result has to be only along L. And by the way, if I write LA and I pull the index A back, what is that? Just 0, right? So that's why the L being down, I pull it back and it doesn't really help. Right? So that's why this has to be only proportional to L in this case. So this defines this one form omega just from the condition of 0 expansion, shear, and twist. And this plays a critical role in the whole theory. And you can notice here from this definition of the surface gravity that in fact the kappa is LA omega A. I can just contract this, so I can contract the index A with the L. L is tangent to the horizon, so I'm allowed to do that. So the contraction of that with L, that is simply this left-hand term here. So therefore this is simply L times omega, so that is the surface gravity. Okay. Then we can go further. We can now check that the Lie derivative of the QAB is the degenerate metric on the horizon. Okay, so we will have, the notation will be that on this horizon there is a metric QAB, which is degenerate, it has a null direction. And on any cross section, I will call the metric to be Q tilde AB. So that is a two-dimensional metric, that is Riemannian. Okay? So here I'm referring now to the degenerate metric Q. So this, the Lie derivative along L of the Q has to be, right, so symmetrized. And this we see that if I just pull the index down, the pullback is 0, so the Lie derivative of the metric has to be 0. And in fact, what you can do is now for the volume form to calculate areas, you can, for each of these cross sections, I have a Riemannian metric. And I have some, coordinate system, so that therefore I also have a volume form epsilon tilde AB on each of these cross sections. If I integrate that, I get the area of the cross section. Okay? I can also show, in fact, that this must also be time independent. And this is, in fact, the reason why no matter what cross section you take, you get the same area. If I just integrate this, then Lie derivative of the area is just 0. It doesn't matter how I change the slice. It still has to be true. So now let us deal with so I told you that the L can be rescaled, right? So at the moment I haven't fixed the rescaling freedom in L. Okay. So then let me now start, maybe it's too far here, so let me start again there. Where is the, okay, so then we have this condition here. So now you realize here, we will realize in a minute, that if I change the L, if I say that L tilde of A, which is F times, or let's say L prime, okay? So F times LA. So F should be positive, but apart from that, there's no, it should be smooth and so on, but there's no other restriction otherwise. This is completely valid. So far, nothing in the non-expanding horizon restricts us to any L, right? I can scale my L as I like. If I do that, the omega corresponding to the L prime will be some omega prime, which will be different in general from omega. Okay, so let us say that grade L prime B is omega prime A L prime. Okay. So if L prime is F times L, so let us put that in here. So this is then F times grade A LB plus LB grade AF equals F omega prime A L. Okay. So let me cancel the F, write the F here. Let me cancel the F. This is just omega A. So index A is always pulled back. Okay. So that's omega A LB plus, this is now the Lie derivative of the function log of F, in fact. And there's a LB everywhere. Wait, there's a little. So this is not the Lie derivative, sorry about that. So this is LB times, this is just the differential, okay? So grade A of log. Okay? And there's a LB here. So take out the LB, then we get the condition that I wanted, which is that omega prime A equals omega A plus, let's call it so this should remind you of a gauge transformation now. So if you think of in electromagnetism the vector potential, if I make a gauge transformation, I add to it a gradient of a function. So in fact, the omega A is just like a gauge field in that sense. And it is in fact a connection one form on sort of the vectors along L. But no, we won't explore that further here. Just to notice that this is how the omega transforms if I change the L, if I scale the L by any function. Okay. So now let us come to the other point that we discussed sort of extensively in the previous cases, which is what is the induced connection or the derivative operator on this non-expanding horizon. Okay? So on the full space-time, we have the connection, the covariant derivative like this. The question is, do we also have a covariant derivative on this null surface? And if you remember what we talked about in the first two lectures, which is that this is not guaranteed. For this to happen, I need to split the tangent space to this submanifold, which in this case is delta, into orthogonal part and the tangential part, right? So let us sort of explore that, right? So the question is, does this reduce, when I pull this index back, to some derivative operator D on delta? So this is the question. Okay? So if I pull this back, then does it give me a derivative operator here? And it's not obvious that it should. Okay, so let me just walk you again through the same reasoning that we did in the first two lectures. Okay? So look at any point P on the horizon. I want this to be sort of, let's say, P on the manifold, the P being on the horizon. M is a full manifold. Okay? So is it true that this is equal to TP tangent space to this horizon, plus the direct sum being some TP perpendicular to delta? But this is not true here, because TP perpendicular are the null normals, and these are tangent to the horizon. So in fact, this TP perpendicular to delta is a subspace of the tangent space to delta. Right? So in fact, this direct sum is just a three-dimensional space, while this is four-dimensional, so they cannot be the same. Right? So therefore, it means we cannot do the split. Therefore, in the standard way, we cannot say that this will reduce, this will determine automatically what this is. You could phrase the problem a bit differently. You could say, well, that's maybe all fine. Maybe I don't need that. I do have the metric on delta, this metric Q. Can I just find the Christoffel symbols connected to this metric Q? You can in principle, right? So let us see. Now repeat now the same thing that you might have learned in GR about how to get the Christoffel symbols from the metric. Right? Then you might say that, well, what I want is I want to say that dA of some vector xb should be the partial derivative minus this Christoffel symbols a, b, c, x, c. Right? And you can say I want to find this Christoffel symbol such that dA of qbc is 0. Right? So this is what you do in your standard GR course, right? This is how you get the equation for the Christoffel symbols, right? So let us see what that implies. You can do the same thing here. So let's say we did that. Then what you will find is the following. You will find this relation here, which is that QCD gamma DAB equals 1/2 So you will find with the standard manipulations like you do in the usual GR case, you will find expression of this kind which should determine gamma with these gammas. These terms you will see are exactly like in the Christoffel symbol. Okay? The problem now becomes, for the next step in the standard case, you would take the inverse of the metric and apply that here. The problem here is that the inverse of the metric is a complicated thing. It's a degenerate matrix, so you cannot invert it normally. No, here it is a full 3 by 3. When I have to have a Q tilde, that is the 2 by 2 part. And the claim is that can I find the three-dimensional Christoffel symbols just based on the metric Q? And I want to say that, well, you cannot because of this problem here. The standard thing you learned for the Christoffel symbol doesn't apply here because I cannot invert this metric. So in fact, the gammas are not unique. So I can always add to it something proportional to L and still get a valid condition on these. Okay. So what we have to do is something more sophisticated. We have to sort of follow this logic here in a slightly different way. Okay. So let me now explain that in the remaining 5 minutes. And as usual, I did not complete what I had in mind for this lecture. I will not be able to do it, but fine, as long as you understand it. Okay, so what you want following this logic is a four-dimensional vector space here, right? So what you want to choose is what is called, what you might call a transverse vector space. So you want to say that TP at M should be TP of delta, and the direct sum of, let's call it T tilde of delta at the point P. So this is now meant to be a vector space that is transverse to the horizon, not tangent to it. Okay? How would you pick that? So let's say that this is, let me again draw the horizon here. So the L vector goes along here. So now each cross section, if you remember, has two null normals, L and the N, right? So if I choose a null normal, the other null normal N, that will be inward pointing, then this vector space TP tilde is the vector space along N. The problem is that I can choose any cross section I like, and each of them will give me a different N. So in a sense, this vector space is not unique. To specify this, I need to specify cross section of the horizon, that gives me an N, then this is then the transverse space to the horizon. So this means that if I take any vector field now on the full four manifold, XA, so I can break it up into a parallel part, tangential part, plus let's call it a transverse part, X tilde. So this X tilde should be in this space, this should be in this space, but this space is not unique. It's only transverse, there is no orthogonality here. So therefore, this is not unique. It seems strange, but it is how it is. So therefore, when I want to do this combination here, grad x, y, so this should be, let's say, dx, y, which is the tangential part, plus something along the other part, right? Something along n. So as long as this thing is not zero, then I cannot, in fact, do a decomposition like this. Now, the only time when this works is if, for whatever reason, this vector field for any x and y is always tangent to the horizon. Then there's no need to do this decomposition because then it's always part of this space. This doesn't matter. Then we can ask whether, in fact, this is always then tangent to the horizon or not. In other words, we can ask if LA dotted with this well, but this in fact is true. Why? Because this is simply grad x of, I can just take the y outside and the L inside. So let me just do it slowly. So then this is negative of YB grad X of LB. And this, in fact, is YB XA grad A LB. So this is just the pullback of grad A LB. But since we just saw that the L is expansion free, shear free, and twist free, this whole thing is zero. Therefore, in fact, just as it wasn't obvious, but in fact, it is true for a non-expanding horizon that in fact, you do get a unique connection on the horizon, the D, which is the restriction of the space-time connection, but it is not determined by the metric on this delta. Okay? So then the answer to the question is that, well, indeed, if I pull back this index A, then I do get a well-defined derivative, covariant derivative on this null surface, except that this is not fully determined by the metric, the Q. So this means that the data on the horizon is not just the two metric, but the part of the connection which is not determined by the metric, which happens in fact to be this omega. Okay? So then the data to be specified on a horizon is not just the metric on the horizon, but the metric and this one from omega, which is a part of the connection which is along the L direction, which is not determined by the metric. So that is then the end result of this analysis, which is that the data on the horizon is the metric and this one from omega. So given these, I know all the geometry of the horizon. So it is not just the metric that I need for this. Okay, so we'll continue this further, and we are not done with non-expanding horizon. There's still a lot more that holds on non-expanding horizons. So that will continue tomorrow. And we'll then restrict the condition more and more and get to the case when we can show the laws of black hole mechanics eventually. Okay, good. So then see you tomorrow.